Welcome, everybody. It's my pleasure to introduce Giga Verk, who will be speaking on Hausmann's conjecture and in particular a counterexample to Hausmann's conjecture. So Giga, please take it away.
Okay, thanks, Henry. Thanks for the introduction and welcome everyone. Today, as Henry mentioned, I'll be talking about the counterexample to Hausmann's conjecture. And I got an instructions that the talk should not be too long. So the idea is to have a discussion. So at any point, you should feel free to interrupt me and ask some questions. Okay, so let's start with the conjecture. So throughout the talk, we'll be talking about closed connected Riemannian manifolds, although you can, in general, also consider more general spaces. But since we'll be looking for a counterexample, the nicest possible counterexample is a closed connected manifold. So that's what we'll focus on. So the main theorem that started this thing is the theorem of Hausmann. It's the one that Henry already mentioned. So the theorem states that for X, which is a closed connected Riemannian manifold, or actually the theorem is originally stated in a bit wider sense, the Rips complex of X at scale R reconstructs the homotopy type of X for small scales R. So here in this definition, I'm using open Rips complexes. I should point that out. And then in his paper, Hausmann has two questions, conjectures kind of. So the first one is whether the homotopy type of X can be reconstructed through the Rips complex on finitely many sets, on finitely many points. So that's the problem that's been solved by Lacho. And then it's later been generalized in more computational setting. And the second conjecture, the one we'll be talking about today, is the following. Is the connectivity of the Rips complex an increasing function of R? So what does Hausmann mean by that? So simplicial complex, or space in general, is n connected, where n is a natural number, if the first n homotopy groups are trivial. So this conjecture actually states that, well, as R is increasing, this n connectivity parameter should also be a non-decreasing function. So increasing potentially, but especially it shouldn't be a decreasing function. So this conjecture has been supported by, up till recently, by all known examples. So Hausmann provides a few examples, and then Henry has a bunch of papers where he's dealing with Rips complexes of circles, ellipses, and similar things, and the same pattern appears everywhere. Then there are some results where you can determine the Rips complexes of wedges or some metric gluings, and everything seems to work. The conjecture seems to work in those examples. So today we'll, well, as was announced, the main goal is to present a counterexample to this behavior. So essentially, we will want to present an example of a space in which homotopy elements appear in Rips complexes at higher scales. Okay, so let's try to think first a bit about where a counterexample could be found. So of course, we are not going to get anything in dimension 0. Everything is born essentially at the beginning. Since our space is connected, no component is born later. Then the second, well, the first serious contender would be the first homotopy group, meaning the fundamental group. And it turns out that the fundamental group respects Hausmann conjecture in the sense that these bonding maps, where R2 is larger than R1, are always surjective. And actually, the, so to speak, persistent fundamental group and also persistent first homology group of geodesic metric spaces are perfectly well understood. They are known to encode shortest homology or fundamental group base. And for example, if you have a torus like this, the first barcode, so to speak, would look something like this. So all bars start at the beginning and then they start dying off at thirds of the lengths of the corresponding generators. All right, so we cannot find a counterexample by treating just first groups, meaning fundamental groups, which means that we have to turn our attention to higher homotopy groups. So our counterexample will actually be provided by treating the second homotopy group. And it will turn out that, well, essentially we will, our counterexample, I can say it now, it will actually be a three-sphere. Now, there's a question whether a counterexample could be found by treating two-dimensional homotopy group on a surface. Now, I'm not sure whether that can be found. Just judging by my intuition, it appears that the second homotopy group of the surface might respect Hausman conjecture, meaning that nothing is born after the fundamental class dies out. Well, fundamental class is a homological feature, but essentially you could also state the Hausman conjecture for homology groups as well. Yes, in the conjecture, so there's a question, is the conjecture is R unbounded, or is it still bounded above by R, by capital R? Let's go back. Yes, in the conjecture, R is unbounded. I mean, if it's bounded above by R, we know that for these scales, you get a homotopy equivalence. So the question is, what happens when you go beyond this R? All right, so this was a question from chat. All right, so as you mentioned, counterexample will be provided by treating a second homotopy group of a three-sphere, and it is unknown whether a counterexample can be found, which is just a surface. By the way, in the previous two talks we had, we heard several results that were actually talking about the fundamental class of the surface dying out. So Facundo was connecting it to the filling radius, and Baris was also talking about some thin thick decompositions and some widths there. So there are some connections there, but it's not clear at this point how it should be done. All right. Is there any question at this point? Okay, so on this slide, I'm going to essentially give you the whole counterexample. And then after that, we'll have 4 slides of just polishing out some details, which are interesting problems in their own self. So the crucial idea is the following. For each positive epsilon, we want to find a geodesic distance on the three-sphere, which is so that the three-sphere with this geodesic distance is epsilon close to the standard sphere. So as to, if I'm not stating a metric specifically, this is just a standard sphere, although formally you could just take any fixed sphere with a geodesic distance, of course. Okay, now how do we find such a metric? We'll discuss that later. So for the time being, let us just assume it exists. Now we can combine the Hausman's result for the two-sphere, which states that for small r, the persistent homology of the two-sphere is just you just have one bar in dimension 2. Let's talk about reduced homology. Let's not consider a zero-dimensional homology. And then after R, all sorts of things can start happening in this gray shaded area. And the same thing happens for three-dimensional sphere, right? So this capital R can be a bit smaller, but the point is still the same. Hausmann's theorem states that initially we get the Rips complexes attain the homotopy type of the three spheres, and later all sorts of other things can start appearing. Now, if we combine these two persistence diagrams with our assumption and the stability theorem, we see that a two-dimensional bar should also appear in persistent homology of this thing. So what's that? I mean, this is the standard stability theorem, right? If you have two spaces which are at Gromov-Hausdorff distance most epsilon, then the distance between persistence diagrams is at most 2 epsilon. All right, and this picture actually provides a counterexample to a homological version of Hausmann's conjecture already. We have for small r's, we see that the Rips complex of this space is two connected. And on the other hand, the appearance of a two-dimensional homology element suggests that later the complex becomes only one connected. So we get a decrease in the connectivity parameter. Now, of course, these pictures only represent homological versions, although one can easily use standard approaches of algebraic topology, so use universal coefficients theorem to see that there exists a persistent feature in second homology with integer coefficients. And then you also use the Whitehead theorem, which tells you that the second homotopy and homology groups are isomorphic. Why is that? As we mentioned earlier, we know that all these complexes are simply connected. If you recall, the induced maps on fundamental groups are surjective. So everything works out. The second homology and homotopy groups are isomorphic, and we essentially get two-dimensional persistent feature in the second homotopy group. So this is essentially a counterexample. It's a fairly simple one. All right. Is there any question?
Yeah, can I ask a clarification question? So, I mean, the barcodes in the white regions, you're saying you know the barcode exactly. And then in the gray regions, maybe you're just saying you know some things about them. So the important thing is that you have nothing below dimension 3, but then something appears in dimension 2. But you might not know that the 3-dimensional bar and the 2-dimensional bar, for example, overlap so much, or things like that.
That's right. Yeah. You don't know anything about the overlap. Yeah. I mean, this is just,
picture. Yeah.
Yeah. But even if they don't overlap, I mean, it is a counterexample to that thing. So, yeah, of course, there's always this question of quantifying about how bad does the situation get. All right. Any other question? All right, so this is the main argument. We skipped a few details that we should probably discuss. And actually for the rest of this talk, we'll be just discussing them. So first of them is we actually need persistent Hausmann's theorem to pull off this argument. Why? So Hausmann's theorem just tells you about the behavior of a Rips complex at a certain scale parameter. It does not tell you whether those features persist. So for example, Henry in his paper on Vittorius Rips complexes of ellipses, he finds this interval on which the Rips complexes are actually wedges of 5 spheres, but only one of those spheres is persistent. So, you know, it's not apparent that everything will persist as it should. I mean, it turns out that it will, but in general, that's something that has to be discussed. And of course, the second question is, well, how do we find a metric like this? So we'll discuss these two questions next. All right. So in order to discuss the persistent version of Hausmann's theorem, we'll go ages back and start with a very topological approach. So let U be a cover of a space X. Here in our example, we have 6 points and 4 sets. And then given a cover, there are two, I want to say natural, but they're not categorically natural. I would say they're very obvious complexes that you can build. One of them is the original Vietoris complex, which consists of all, it's a complex whose vertex set is essentially X as a set, and consists of all finite subsets which are contained in some element of our cover. So essentially, each element of our cover provides us with a maximal simplex. And then the same with this one. All right. So as we said, we start with a cover of a space, and we build a Vietoris complex. So in the Vietoris complex, the sets actually provide maximal simplices. And then the second complex is the nerve complex, which is a fairly well-known construction. And then, of course, there are some theorems that relate all these constructions. So the first one is the nerve theorem. If U is a good cover, it means that we have a homotopy equivalence going from our space to the nerve. So this homotopy equivalence is based on partitions of unity. And the second relationship here is the Dowcar duality. So the Vietoris and nerve complexes are actually homotopy equivalent. That's something that's actually, that's been proved by Dowcar in the 50s, I believe, of the previous century. But it's something that's actually, for which there is a fairly easy proof. If you consider this maximal simplices as a cover of the Vietoris complex, then the nerve of this cover is precisely the nerve of your original cover. And this cover is good. Well, it's not open, but you can thicken it a little bit. So, I mean, that's a technical detail that can be polished. So essentially, this homotopy equivalence is just a special case of the nerve theorem. All right, and why are we interested in all these constructions? Well, the Rips complex is actually a Vietoris complex, and that's actually the reason why I, at least in this presentation, I prefer to use term Rips. So Vietoris originally defined complexes in this setting, and Rips complexes are essentially just a metric version of Vietoris complex. So in the same setting, the nerve complex is a complex arising from covers, while the Čech complex is a specific nerve complex arising from the covers with open balls. So it turns out, well, it's actually easy to see that Rips complex, so if you recall, a finite collection of points is a simplex in a Rips complex if and only if it's of diameter less than r. So that means that if you take a collection of all subsets of diameter less than r, its Vietoris complex will be the Rips complex at scale r. Now, the collection of all subsets of prescribed diameter is, of course, not a good cover. You can have discrete sets, of course. So in general, when you want to connect that with nerve theorems and so, you want to find a cover so that all finite subsets of that cover, meaning all sets of this sort, are precisely sets of diameter less than r. So we'll construct an example like that later. But the point is here that actually with this connection, you can connect the RIPS complex to the nerve construction. All right. So my next slide, I will, yeah, by the way, is there any question? Okay, so in my next slide, I will just keep this left part with definitions and rephrase these pictures with diagrams. So it turns out that if you have a map of spaces and covers U of X and V of Y so that F of U, essentially, this should be F of U, is subordinated to V. So essentially, if you have nested covers in a way, you can construct this diagram that commutes up to homotopy. So I typically call this Dowker nerve diagram. So spaces are connected to their nerves, and then this thing on the right is the Dowker duality connecting nerves to their Vietoris complexes. And the fact that this diagram commutes follows essentially straight from the definition and contiguity. All these maps arise from partitions of unity, and once you just write that down, it's fairly easy to check that everything works out. So in our setting, what we want is, of course, we want to reconstruct RIPS complexes and see that those homotopy equivalences are functorial. So if we can construct good covers UR, then taking an identity here, these two maps will be homotopy equivalences by the nerve theorem. By the commutativity, this vertical map will be homotopy equivalence. And then composing with Dowker dualities, which are homotopy equivalences arising from those partitions of unity, we will get that this inclusion is also homotopy equivalence. All right, so in order to prove a functorial Hausman theorem, we just need to prove that UR can be chosen so that it's a good cover, and of course it has to be nested. But then again, for larger R, UR will consist of larger sets, so nesting is kind of for free. All right, is there any question at this point? No, okay. So my next slide, we will actually construct UR for our space X, so closed connected Riemannian manifold. And I will keep this question, this property of RIPS complexes, and just the definition of Vietoris complex. And we keep in mind that in order to prove persistent Hausman theorem, we just need to choose good covers. Okay, so X is a close connected Riemannian manifold. We won't go into technical details of Riemannian manifolds. We will just use the property of these manifolds that have also been used by Hausman. Now, there he defines something like some sort of injectivity radius. It's a bit slightly different. So we're not going to use precisely his definition. I'm just going to rephrase slightly weaker definition that arises from his conditions. So Hausman says that given X, there exists a capital R, so that for all R smaller than 0, 3 conditions hold. First of all, if the distance between points is less than R, then there exists a unique geodesic between these 2 points. So that's a fairly natural condition. The second condition here states essentially implies that if a subset of X is of diameter less than R, then taking its convex hull does not increase its diameter. So what I wrote is slightly weaker, but it doesn't matter. I mean, that's all we need. So the only thing we need is that taking a convex set in this local setting does not increase the diameter. And the third condition, well, the condition that follows from his third observation is that if A is a subset of diameter less than R, potentially discrete, so it wouldn't be contractible, then its convex hull, which is again of diameter less than R by point B, is contractible. So Hausmann's conditions are a bit more geometric in the sense that he's using geodesic distances and triangles and things like that. But essentially, these are the properties that follow from his conditions. All right. So given these properties, we want to define good covers, UR, and obviously the natural choice is just the collection of all convex hulls of sets of diameter less than R. So why is that? Well, any sigma in R, which will be of diameter less than R, will be contained in one of these sets. You can just take the convex hull of that set. And on the other hand, if a finite subset if you have a finite subset of such a set, well, then by part B, this finite subset has diameter less than R. So finite subsets of these elements of the cover, of this cover, are precisely simplices of the Rips complex. All right. And then you just use standard convexity arguments. So convexity in this sense means geodesic convexity, like in Riemannian manifolds. All right. So you have a cover by geodesically convex sets. All the sets are contractible. Their intersections are also either empty or geodesically convex, which means they're also contractible. So this is actually a good cover. And that's it. I mean, with this, you prove, you essentially prove persistent version of Hausmann's result. So how does that look? So if you have, let's say, 3 simplices in a Rips complex, each of these finite collections of points is not a contractible set, but you just complete them to a geodesically convex set. So in flat manifolds, you would see something like this. If you have perhaps hyperbolic manifold, you would see something like this, but by geodesic convexity, everything still works out. So essentially with this, we have proved, we have provided a short proof of Hausmann's theorem, and actually also its persistent version. All right, is there any question at this point? No. All right. Okay, so this was the first thing that needs to be discussed. And now to the second thing. How do we approximate the 2-dimensional sphere by a 3-dimensional sphere? Now, in this occurrence, we're just going to take the easy way and just pick a result. So it's a theorem by Ferri and Okun, which coincidentally has been published in the same year as Hausmann's paper. And their purpose was actually precisely that. So you want to approximate metric spaces by Riemannian manifolds. So here's the statement. Suppose M is a smooth connected manifold of dimension at least 3. So here's another reason why surfaces wouldn't work for our argument, as we discussed earlier. Suppose X is a geodesic space, a target space, and suppose you have a map with connected fibers. Now, in their theorem, they have a slightly more general condition, but as stated, suffices for us. Now, then there exists a sequence of Riemannian metrics so that M with this matrix converges to X in Gromov-Hausdorff distance. So this is something like we would want to use. So let's recall. So we want to approximate S2 by matrix on S3, which means that, well, we need to have a map, surjective map from S3 to S2 with connected fibers. So that's a quick quiz question. Of course, you choose the Hopf map. What else would you pick? And that completes the argument, essentially. Now, if you want to imagine these things geometrically, so how could we see it? A Hopf map actually provides a fiber bundle which decomposes S3 locally as S2 and S1. So if you change the metric locally here so that you keep the original distance on the S2 on this base space and just keep decreasing the distance essentially on the S1. So that would mean that, here you have S2, and as for S1s, you're just shrinking them. You'll keep getting something you'll get something that converges to S2, of course, somehow. So this is the geometric idea of why this thing works. All right. So that's it. These are the
and Giga, there's sort of a statement or a question in the chat about that approximation. So Matthew Wintraken says, I presume the curvature blows up here.
Yes, of course, yeah. So of course, one of the quantitative questions here would be, if you want to control the curvature, how close can you get? So curvature here, yeah, this. I don't think that can be avoided, but I think it would be interesting to quantify it, how bad can it get? All right. So with this, we concluded our argument. So we proved that we disproved the Hausman conjecture persistently. So not just that there exists higher R, scales R where things fail, but actually there are persistent features that make it fail. An interesting observation is that our arguments actually show that if you take any sphere with a geodesic metric, it can be approximated by Riemannian S3 sphere, right? So that essentially means that if you take a collection of all possible persistent diagrams of a single two-sphere or all spheres, well, they lie in the closure of persistent diagrams of three spheres. So of course, this is another direction of thought that, well, how can you compare the collections of these persistence diagrams? So as soon as you have surjective maps, as in this Ferry-Okun theorem, you have a containment like this. All right, Henry said I only have 35 minutes, and I'm taking Henry very seriously. So this is all I had to say.
You're the first one, Giga, to complete the difficult task of giving a 35-minute talk. But thank you so much for the beautiful talk. Before we get to more questions and discussion, let's unmute ourselves briefly and applaud for Giga. So further questions for Giga?
I have a question. I think I missed the, so this was all about homology, right? And you also mentioned this, the original statement was about homotopy groups.
Yeah, I mean,
may-
it's actually,
The- But the point is the argument applies to in either case, right?
well, this is the
yeah.
homological part, and by the universal coefficients theorem and Whitehead theorem, you have this persistent element in pi2 as well.
I'm confused. This should be, I mean, universal coefficient theorem. What is the argument here?
Well, the argument is that here you get, I mean, essentially, there's a workaround. You can just go directly through interleaving on homotopy groups. But the argument here is that here you get a persistent feature with coefficients in any field. And that gives you essentially a persistent feature in coefficients with integers.
Yeah.
And then the second homology group by the Whitehead theorem is isomorphic to second homology and homotopy. So the second homology and second homotopy groups are isomorphic because both spaces are simply connected.
Okay, this is, I would expect that this is Horevich, but is this what you mean?
Horevich, sorry. Yeah.
Okay.
Oh,
Now I
sorry,
understand. Okay,
sorry,
I was just puzzled by the name right then. Okay, thanks. Yeah.
My bad. Sorry.
Okay, thank you.
And Matthew has a question.
Yeah, so I was wondering more about this curvature bound. So, of course, the Gromov-Hausdorff distance is, well, one of the equivalent definitions is via an embedding and then taking the Hausdorff distance. Would you be able to do it with an embedding into a nice space such that the reach of both of them can be, well, controlled in a reasonable way?
I think that's a very good question. I haven't thought of that. So, no. So at no point have I included the reach. I wouldn't have anything smart to say about that.
Yeah, I mean, it's clear that it seemed clear, and you confirmed that the curvature needs to blow up. But I think that if you do it via Gromov-Hausdorff and you embed in a metric space anyhow, then the next question is obviously how to do it with a bounded reach, or control the reach in the same way as you want to control the curvature.
Yeah. Yeah. Yeah, so that would be a different question. So the first one would be if you want to control the curvature, how bad can it get? And the second one by controlling the reach, yeah.
Yeah, I mean, the second one obviously implies the first, but...
Yeah, of course, yeah.
Yeah.
Yeah, I don't have any intuition, but it's a good question, yeah. So actually, I mean, I think this approach opens up a lot of questions in various directions.
Okay, yeah, I would be interested in the result. Should you ever go and look at that?
You mean in terms of reach?
Yeah.
Yeah. Okay. Yeah,
also the curvature, but there it's more straightforward, I think.
Mm-hmm.
Thanks a lot.
Yeah. Thanks.
So I think Barish has a question.
Hi, Jiga. A great talk. Thank you very much. So I just wanted this, is Hausmann's constant capital R is changing with the metric. If the so can you go back to this same slide?
Yeah.
Capital R here corresponding to S3, D3. Is it changing with the metric? And if yes, how do you make sure that little r1 is smaller than capital R here?
Oh, so you want this? No, wait, sorry. So you're talking about this argument, right?
Yeah.
Yeah. So can you state your question again?
So if you have a capital R in the right, the gray box, right?
Yes.
Capital R coming from, so if capital R is changing with the metric SPD3, how do you make sure that the distance, the Gromov-Hausdorff distance epsilon is smaller than capital R?
I don't care about that.
I don't know. Is it topological argument, this Hausmann's conjecture, or is it changing with the metric? That's my question.
So the R from the Hausmann, so this bound changes with the metric, of course. So it depends on the curvature, amongst other things. But for my argument, essentially, this argument essentially implies, well, Hausmann's argument implies that if the Gromov-Hausdorff distance is less than epsilon, well, let's see, what does it imply? It tells me that that R here should not be larger than 2 epsilon, essentially.
So my question is, why does it in the left side of the capital R, not in the right side?
Oh, you mean this one?
Yeah. Why is it smaller than capital R?
You mean capital R here?
No, in the right on the box, right side of the box. So Hausmann's theorem tells you up to some capital R.
Yes.
You are close to the original topology.
Well,
you are using
the stability. Well, Hausmann's theorem tells me that I start with something like this, that with just a 3-dimensional bar.
Yes.
And then stability theorem tells me that I need to have a bar somewhere here, within 2 epsilon of this bar. So by Hausmann's theorem, this bar here cannot go to 0.
Okay, yeah.
So in these pictures, I'm combining Hausmann's, well, persistent versions of Hausmann's results and stability results. And combining them both, they tell me that this bar cannot begin before the capital R for this space.
Okay, thank you.
So I hope I answered questions.
Yeah.
So if not, please let me know.
More questions? I have maybe a 2-part question, Giga. So some of your earlier counterexamples to Hausmann's conjecture involved manifolds with boundary. I was wondering if you could remind me of what that was again. Was it a 2-sphere with like a cap cutoff, or was it a 3-sphere? I think. And then the second part question is, I really love this proof. How did you find this paper by Ferry and Oakland that you use? Is this something that you already knew about and is well known in your community, or what was the intuition that led you to find?
I mean, it was essentially, it kind of started with this example. So let me give you that example first. So the original counterexamples that I was talking about was a cutoff sphere. It's a 2-dimensional, well, no, that's not a good thing. So it's a 2-dimensional sphere. And of course, because it's contractible for small r's, well, the Hausmann's theorem doesn't really imply it directly, but it should be contractible for small r's. While for some larger r's, once you fill this thing up with a triangle, a 2-dimensional thing appears. So actually, in my previous ATNR talk, I was talking about how various persistent homology features keep appearing. So 2-dimensional things appear. So this is kind of similar to Joran works of yours and Barry's. And then also three-dimensional features start appearing here, just from the circle. And then when we wanted to write it down formally, I mean, there was this idea that, well, you can compute it. And in some sense, the easiest way to prove that this two-dimensional thing appears was just by saying that, well, this is very close to a sphere, right? So this cutoff space is very close to a sphere. And of course, well, if something two-dimensional appears here, if you make this hole small enough, well, it should also appear here. So the original arguments about the appearance of two- and three-dimensional elements are more general. They work in a more geometric setting, but just for the case of a, if you just want a simple counterexample, then this is probably the shortest way to go. Although in general, I mean, of course, if you want to prove something like this happens on torus, you cannot just map a sphere there or something. There are other issues. So I hope I answered some of the questions.
Could you say a little bit more about this Ferry Okun paper? Have you known about this for a long time, or did you?
Oh, that one, sorry. Yeah, no, I found out about it like a couple of months ago, maybe at the end of the last year, when I was just thinking about how to do it. So it's not something that I would have been familiar with for a long time. It's a recent thing for me.
So another question. So all right, so this picture, you go from contractible, which is sort of homotopy, connectivity, infinity, right? To then you have sort of this pi2 that appears. So it's now only one connected. But before this really nice hop argument and using Ferry Okun, right? You were thinking for counterexamples along the lines of taking a four sphere, I think, and then pretend you can find a circle in the four sphere. I know the equator of a four sphere is a three sphere, but pretend you can find a circle in the four sphere that you sort of like shrink down.
Yeah.
And that circle leads to an appearance of a three sphere. Do you think proofs like this are possible? Or do you think proofs like this are very hard? I'm just curious to get your thoughts on that.
I think that proof still works. So that's along the lines of my previous work, what I did. So this argument, as I presented, in a way arose from the fact that, polishing out the details of this kind of proofs is hard, right? I mean, either you want explicit construction, or in order for those conditions to work, you need to be able to push these things down and control the distances and stuff like. So I'm absolutely certain those things work. It's just that, writing down an explicit example is kind of hard. So when I came up with this a new way of generating higher dimensional features with this Gromov-Hausdorff closeness, and then I saw this Hopf argument, I mean, it's just, you can see it, right? It's almost in 3 dimensions. So this one still works. I mean, I'm pretty sure it still works. But I don't feel very motivated about polishing the details yet. But yeah, that was the first example we actually talked about a while ago.
More questions from folks?
Yeah, if I can. So I would like to know, have you thought maybe if other Hopf vibrations work in the same way? Like, do you have a similar scenario?
Yeah, so, oops. This argument, in a way, would work for, so this Ferry-Hopf theorem. This would work over other maps as well. Yeah, so whenever you have, I mean, not just Hopf vibrations, but over other spaces as well. So I only presented here the example here of S2 and S3 because it's the minimal dimension-wise example that I could make it work. So Henry, that's another example why I went for this one. It has smaller dimension than those 4-dimensional spheres. But yeah, the argument essentially would work for other Hopf vibrations as well.
Okay, yeah, so basically that's the only result that you need to have like exactly the same, because the other parts work in the same way for the other Hopf vibrations.
Yeah, that's right.
Okay, thanks. Thank
Or
you.
even more general maps.
Thank you.
Yeah, thanks for the question.
More questions?
I have a question slash comment. In a paper by Adamaszek, Adams, and Frick, they do this like Hausman theorem for the metric thickening.
Mhm.
And if I understand things correctly, that one is already persistent because they kind of have like the map from the Vittori scripts thickening to the original manifold is like a deformation retract, and it should like
Mhm.
respect kind of the persistence.
Mhm. Okay,
So,
but
I mean,
that one doesn't imply this one yet, right? Not to our
Um,
best knowledge, Henry, or how? What's the situation?
Yeah, connections between the Viator-Ship simplicial complexes and metric thickening are known at the homology level, but not at the homotopy type level.
right. But since, I mean, the argument that you give uses just homology. I mean, I'm not saying that this proof is simpler. I'm just saying that it's interesting that that explicit construction, if I'm not mistaken, is already persistent thanks to like having the metric that lets you retract it.
Yeah, you mean on metric thickenings?
Right.
Yeah. Yeah. So possibly with this equivalence of homologies, that one could be used as well. Yeah, that's. I agree with that.
More questions?
Okay, should be better.
Well, if not, let's end the recording here. So thanks very much, Giga, for the fantastic talk, and thanks everybody for all the questions and discussion and ideas.